Welcome to the class of material selection for mechanical design. We have looked into most of the important points when as a designer you have to choose materials. Okay, we have talked about stiffness, we have talked about strength, we have talked about fracture, we have talked about fatigue and also hardness. So these are the basic elements, but still it is not over. We still need some more points, mechanical properties to consider before we take a look into finalization of our product material point of view. Okay, so what is left then? Well, we have not considered the most important case, which is the vibration. Many of the mechanical system will be subjected to either a long term stretching called creep, and also related to that a property called relaxation and vibration, which can be either dampening in nature or it will be reverberating in nature. So depending on the applications, for example, if it is a musical instrument, you want the structure to have as low vibration as possible, as low damping as possible, so that you get a continued vibration in the system. On the other hand, if you are choosing material for a bridge or choosing material for an automobile, you want the vibration to be as low as possible, so that it will be more comfortable and it will not have any catastrophic failure. And hence, this property sets we are going to look into in this lecture and the following lecture with much more details. So, let us look into it. The first point, as I told you, is the creep. Creep is a permanent deformation under constant load over a period of time. So, you see, when we consider a material like say metal, steel, we think that okay, it can withstand the same load for years. Okay. However, what happens is that metals are not the only sort of materials for us. Okay, we use polymers also, and for the polymers, if you think of a day to day experience, that you have these nylon wares what we use for spreading the clothes. Okay. So, now over the time what happens, you would see that the wear gets slackened. Okay. Why? Because under constant load, polymers have the habit of actually relaxing, and then the creep happens in the polymer. Okay, so this phenomena is something which you can see in a day-to-day phenomenon itself on a material like polymer. Does the metals creep? Yes, they also creep, but for that you need to have a higher temperature. If you are closer to the melting point of a metal, let us say how close you are, more than 60 to 70% of the melting point temperature. Okay, so close to 70%. So, let us say if it is iron 1400 and then you are close to say 1000 degrees centigrade, you are definitely going to see that under an applied load, this metal is going to show the under that constant load condition, the deformation is happening. And in a way it actually means is that every material towards the phase change starts to behave like a viscous fluid, and that is why this starts to happen. So, it is heavily dependent on temperature, and creep test involves that is why a tensile specimen under a constant load maintained at a constant temperature, that temperature can be high, but maintain that temperature, and you would see at a relatively high temperature creep appears to occur at all stress level, but the creep rate increases with increasing stress at a given temperature. So, this is important for design of systems like turbine blades, nuclear reactor component, jet engines, heat exchangers, etc. Now, the creep, if I try to look into that, how this creeping is happening, you will see that it has three stages: primary stage, secondary stage and tertiary stage. Okay. So, the primary stage is where the instantaneous deformation happens. You apply the load, you see the instantaneous deformation. After that, the deformation remains almost steady, does not increase much till that secondary phase. And finally, you get the tertiary phase where suddenly the deformation increases at a very high rate. So, at t less than 0.4 tm and after the initial deformation, the strain is virtually independent of time. Okay? And with either increase in stress or temperature, creep strain is going to increase. So, in this case, you are finding that as with the time is changing, with the application of the same load, there is this creeping is going to happen that ends in rupture. And on the other hand, if you look into it from the temperature point of view, you would see that as the temperature is increasing, you are going to see that against the same load, the failure is going to happen pretty fast. Okay? In this case, less than 0.4 of melting point, close to melting point temperature, it is not going to creep at all. So, you will see the instantaneous deformation that will remain steady. But as the temperature is increasing, you are finding that shorter and shorter life of the system in terms of the rupture. Now, how do we compare the creep of a material? So, we use a comparable material called mnemonic 75 as a standard creep reference material. So, with respect to mnemonics, which has or any nickel based high temperature which has low creep as a superalloy, with respect to that we can measure what is the creep in our system. Next is damping. Okay. So, as I told you, from the vibration point of view, damping is enormously important. Okay. So, the way we actually reduce the vibration is either increasing the damping capacity, or if it is at a very low frequency level, then increasing the stiffness, or changing the mass if it is at a very high frequency level. Damping refers to essentially the dissipation of energy from a vibrating system, and the damping force magnitude is generally smaller than elastic and inertia forces. Even if damping force is smaller, it has an important role in terms of controlling the vibration, because even if the force is smaller, repeatedly the energy is getting drained, and that actually makes the shape exponential in nature. This we have to definitely consider for applications where shock absorption is important, fatigue failure needs to be prevented, or noise needs to be reduced. Now, there are different types of damping systems. One of them is called viscous damping. So, this is typically represented by a viscous, a dashpot system. So, which shows a piston which is moving relative to a cylinder containing a fluid. So, such damping force is called proportional to the velocity, CdX dot. Now, what we are going to assume, of course, for this viscous damping case is that the relative velocity is low and there is a laminar flow that is happening in the system. So, this is typically a viscous damper which is used for earthquake prevention. So, this is seismic protection, okay, against the earthquake. So, that is the viscous damping system. What kind of material we will use? Well, some fluids like a viscous fluid like silicone is one of them, silicone oil. So, you can use in terms of damping or dissipating the energy of the system. Then there is another type of damping possibility, that is because of the rubbing of the two surfaces. So, we call it the Coulomb damping. So, dry friction force between two solid interfaces. So, in this case, the magnitude of damping force is assumed constant, okay, that is independent of the relative velocity at the interface, but it is having a direction which is always opposing the slip velocity. So, sine of x signum function we call it equals to 1 for positive velocity, equals to -1 for negative velocity. So, it reverses the direction depending on the direction of the relative velocity of the two systems. So, that is Coulomb damping. And next important point we have to keep in our mind related to damping is the damping ratio. Okay. So, earlier we said that F d is C x dot, right, but that is not good enough. We should always see that what is the nature of the damping. So, that let us say we are trying to measure the response of a system. Okay. Now, if the response is like this, exponentially coming down, so this will be under damped system. For a critically damped system, this will simply come down without any oscillation. So, that will be critically damped system. And if the damping is more, then the same thing will happen without any oscillation, but may take a little more time. Okay? So, that is the over damping system. So, that is over damped. Now, we always measure the damping with the critically damped system. So, Cc is the critical damping, and that is generally defined as 2 times square root of Km. Okay? So, what is the square root of Km? Well, we always look into damping in terms of this simple 3 parameter model. Okay? So, this is K, this is C, and this is M. There are always higher models are also there, I will talk about it later. So, with respect to these single degree of freedom 3 parameter model, single degree of freedom 3 parameter model, now you can easily find out what is K and what is M. And now you also know that for critically damped system C will be Cc. So, the value of zeta will be 1, and for under damped system zeta will be much less than 1, and for over damped system zeta will be much greater than 1. It will be greater than 1. Okay, so that is important, and another associated term here is quality factor, okay, Q factor, which is the reciprocal of the damping. Okay. So, that is that we are going to use this term also soon, and at that time I am going to define this. Now, the loss factor, which is an important element, that is how much energy is dissipated during vibration, okay, and the ratio of that with respect to how much energy is stored into the system in every oscillation. So, you see the loss factor essentially tells us, suppose if the loss factor is 0, then entire energy is stored, hence there is no energy dissipation. So, this is 0 loss factor. Let us say time versus amplitude of motion. Okay. So, let us give it a parameter like x. This is 0 loss factor. Now, if at each and every cycle we see that the amplitude comes down, okay. So, the amplitude is actually dropping down. So, that means that the part of the energy is getting lost in dissipation. So, then the loss factor, so there is some finite loss factor there. Right. So, this loss factor is defined is related with respect to the zeta, the damping ratio, okay, like this, following this relationship, and also the loss factor and the damping ratio are related to the quality factor. Okay. So, for example, I have shown you here that zeta equals to 1 by 2q. In other words, this tells us that q equals to 1 by 2. zeta. That is the Q factor. Okay. So, this is reciprocal of 1 over 2 times zeta. And these zeta and the eta relationship also can be simplified, and that we will look into it at a later stage. So, let us just look into approximate loss factor. Essentially, loss factor tells us that how heavily damped the material is. Well, in that way, aluminum has a reasonably low loss factor, but the highest loss factor is something like the butyl rubber. Okay, so that dissipates more energy than the neoprene, and then the steel, and then the aluminum. So thus the loss factor we can actually sort of use as another quantification in terms of the energy dissipation. Now, we will look into this energy dissipation for the structural materials. That means all over wherever we have to build a structure, the material itself has some capacity of energy dissipation. See, earlier we have talked about energy dissipation happening due to viscous fluid. So, that was the the viscous damping system. Energy dissipation happening due to the relative friction, but the structure itself has some material roles in terms of certain things happening inside the structure that can also create different types of energy losses during vibration. That is important because that itself can be a good source of damping, and hence you do not have to put additional source of damping. For example, here you have seen that to prevent earthquake you have given an additional source of damping, but if the structure itself can prevent it, that is the best. So, we are looking at energy dissipation in structural materials. Okay, so if you have to look into it, you have to look into it from the point of view of the material properties, the geometric property, and the loading. Of course, all three of them are important in terms of how much of damping is going to happen. Well, we all know that for that single degree of freedom system, okay, inertia, that is the mass part, plays an important role, and then stiffness plays an important role, and then we are going to look into the damping. Now, stiffness is sort of imparted through the Young's modulus and shear modulus as far as the structural damping is concerned, and inertia is imparted by the density and cross section of the system. Now, let us look into the damp. So, what are the possible ways in which the structure can dissipate the energy? One of them is called the Snoek effect. Okay, this is named after its discoverer, a Dutchman, Jacob Louis Snoek. Is a mechanical damping phenomenon that occurs in metals with a BCC cubic crystal structure and partially occupied octahedral gaps, and this is a point defect relaxation. Okay. So, this is something that happens in for example, carbonaceous alpha iron systems, in which the carbon atoms are dissolved on the octahedral gaps of the iron lattice, and there you are going to see that there is a damping that is happening because of the point defects that is there in a crystal because of the relaxation of these defects, and this is what is known as the Snoek effect. Okay. So, the Q factor for it is roughly 100. Okay. So, Q inverse is 1 over 100, and already I defined the Q factor. Okay. In fact, there is an interesting relationship between the tan delta or the loss factor eta and the Q factor. So, this is eta. Eta is tan delta. This relationship will derive later on, and that is reciprocal of the Q factor. Now, damping of capacity of structural material may also depend on various internal mechanisms. For example, one of them is a thermoelastic effect. Okay. So, if the material is initially unstressed, a homogeneous stress field will produce no loss, but if it contains some thermal related stresses, then the non-homogeneous the stress distribution will cause this loss. And then there is another possibility, which is the localized plastic strain, that is present of defects like shear bands that can entangle the dislocations, particularly for polymers. So then the localized plastic strain can create the energy dissipation. For metals, the structural damping can happen because of the grain boundary slip also. Okay, so movement of one grain over the other. And then there is sometimes there are materials like ferromagnetic materials where there is a magnetoelastic coupling. So interaction between magnetization and strain. Okay, let us say the structure is in a magnetic field. So then there is this domain which are already magnetized, and as it is vibrating, magnetic particles are moving against each other. That will also create damping in the system. So that is the magnetoelastic damping. So like there are all these possibilities which can generate the structural damping in a system. Now, one important thing here is that the stress play a very important role in structural damping. Okay? Under harmonic loading and low stress level, the energy dissipation can be given by this kind of a hysteresis in the system. So, this is at low stress level, and where this area under the stress strain curve is measured as dm, and that gives us the measure of energy that is dissipated. Now, the dm is actually related to the stress with two parameters, one is j and another is n. So, there are two parameters, j is called the damping constant and n is called the damping index. N is the damping index, which is usually 2 to 3 in the working stress range. So, this is an important way of defining the structural energy dissipation. Now, between a high stress to low stress, the hysteresis shape actually changes. Okay, so, if this is perfectly elliptical for a low stress, for relatively high stress level, okay, so so this is for n equals to 2, and for n greater than 2, this actually takes up the kind of a pointedness that happens at the two ends of the system. Now, one important thing is that dm is independent of frequency. Okay? So, the structural damping, the hysteresis does not change with the excitation frequency. That is a very important point we have to keep in our mind. And you can compare now between the viscous damping, okay, that is the energy dissipated in the viscous damping case, and compare it with the energy that will dissipate in the structural damping case. So, for energy dissipated in a viscous damping case can be written as pi c omega x square. Okay. So, energy dissipation here increases linearly with the frequency, we can see it, and with the square of the amplitude. So, that is the energy that dissipates in case of a viscously damped system. Okay. Now, if that is the viscous damping, what is the structural damping? Let us say if I try to sort of create an equivalence between the two. So, then we know that the structural damping can be written in terms of j sigma to the power n, which can also be separated into two parts, that is j1 sigma square plus j2 sigma to the power n. So, into two different parts, one part varies with n equals to 2 and another part for n greater than 2. Now, if there is a multi-axial case, then of course, this sigma becomes sigma equivalent square over n by 2, where sigma equivalent square can be obtained from these stress constants, okay, stress invariants I1 and I2. So, the material loss factor is dm as 2 pi over Wm. So, where dm is the energy that is dissipated in a cycle, and Wm is the maximum elastic energy that is stored per cycle. So, we should be able to find out what is the material loss factor. Now, if you have a material like a composite, then of course, you have to find it out for each of the contributing material. So, then you have to do it for each of the materials and then sum it up. Now, if you compare the a few common materials, their density, their Young's modulus and the order of loss factor, you will see that the aluminum has one of the least loss factors, okay, followed by brass, followed by steel, cast iron and concrete. Cast iron and concrete has much higher loss factor. That means they will dissipate more energy. Now, we will come to one mathematical case, okay, where I will show you how we can select material for a linear hysteretic damping case. Okay. For linear hysteretic damping, we will assume that the energy dissipated is simply proportional to the square of the amplitude of motion. Okay. So, alpha x square is the hysteretic damping, and let us compare that with the viscous damping that we already said is always pi c omega x square, and we can find out what is the equivalent damping constant. So, if I equate the two, then what happens? The pi c equivalent omega x square will be alpha x equal to alpha x square gets cancelled, and so C equivalent becomes alpha by pi omega. That is what becomes this expression, and alpha by pi, if you denote it as hysteretic damping coefficient H, then the C equivalent becomes H by omega. And now, you can also not only find out the C equivalent, you can also find out the loss factor eta, which is the energy that is dissipated per cycle and divided by the maximum energy that is stored in the system, and that will come out as alpha by pi k, and alpha by pi being H. So, it will be H by k. So, the for a hysteretic material eta equals to H by k. Now, let us say we are considering a single degree of freedom system and we are trying to estimate the structural damping. So, now instead of C, I can write it as H by omega, that is the equivalent. We have just now saw that the C equivalent is H by omega, alpha by pi was H. So, I can write this governing equation as mx double dot plus H by omega x dot plus kx, that equals to the force. Now, you apply x as amplitude x times e to the power I omega t, and in the steady state you try to find out what is x. So, all this e to the power I omega t or j omega t will get cancelled. So, you are going to get an expression of x with respect to the force that you are applying, the stiffness, the mass, etc. And then if you actually find out the amplitude of the x, you will see that it has have the amplitude of force divided by stiffness, and below you are going to get with the help of a non-dimensional frequency parameter, this will be 1 minus omega square plus eta square root. Okay, so, that is what will be the amplitude of displacement. Let us try to find out now the material selection criteria against such a case. So, now we have this x as f by k over 1 minus omega square plus eta square root of it, and let us say omega equals to 1, that is maximum, that is for resonance, right. So, for resonance you are going to see that the x maximum will be related to f over eta k. Let us look further and see what are the material properties that is involved inside f over eta k. Well, suppose we consider a case where we have the width of a beam that is given, okay, and then in that case the stiffness will only change with the thickness. How will it change? It will change with the cube of the thickness. and of course it is K varies with ET cube, okay, where T is the thickness of the beam and E is the Young's modulus. Now you see that for a given specified mass, thickness varies inversely with the density. Okay. So now this stiffness K will vary with what? Modulus of elasticity proportionately and inversely with rho cube. Okay. So essentially whenever we see F over eta K, what the material property that is involved there is E eta over rho cube. Okay. So for structural damping, our material property index will be E eta over rho cube. That is important, for us for structural damping. Let us now look into it, that what will be this value for steel, brass and aluminum. By we know each one of their E's, we know their loss factors, that is we know the eta, we know the E, we know the density. So, we should be able to calculate them, and we can see that way is very interesting, even though aluminum has a higher loss factor, but because for this application of structural damping the modulus of elasticity also comes into picture, steel becomes higher than aluminum. Aluminum is the next and brass is the lowest. So, this is 1, this is 2 and this is 3. So, that is how many times SB index gives us a surprising result, because invariably SB index shows us interplay of 2 or 3 different mechanical properties, okay, and hence we get this interesting result in this case. So, thank you. We will close here as far as the structural damping is concerned. In the next lecture, we will talk about the viscous damping or the viscoelastic damping part of a polymeric system. Thank you.